let's unpack what we mean when we say that there'll be an ice-free Arctic by 2100. And first of all, actually, if we're talking about summer sea ice, we expect it to be a lot sooner than that. And so it's likely that the Arctic will be ice-free in summer, in September, somewhere between 2030 and 2050. So that's quite a lot sooner. And if we're talking about 2100, then we might expect it to be ice-free for several months of the year.
Hello and welcome to this episode of Beyond the Ice, the podcast from British Antarctic Survey where our polar experts unpack the latest news in climate science. My name's Em Newton. In today's episode, we're talking about sea ice again. Earlier this month, the two polar oceans had less ice than ever previously seen in the satellite record. Arctic sea ice has been coming in at its lowest ever extent for this time of year, and in the Antarctic, sea ice is just close to a new record low. Earlier last year, I spoke to Dr Ella Gilbert about the historic lows in Antarctic sea ice, so this time we're talking about just the Arctic. To explain what we're seeing in the Arctic and why, I'm joined by Dr Caroline Holmes, a polar climate scientist at British Antarctic Survey. Caroline, thanks for coming on the podcast.
Great to be here.
Great, so let's go back to basics. What is sea ice? And how is it different to other types of ice that people might have heard of, like a glacier or an iceberg?
So sea ice is ice that forms from the sea. It's in the name. So it's ice that forms when the ocean freezes, and typically that happens most in the winter. So in the Arctic and in the Antarctic, each year as it gets to winter, the surface of the ocean gets very cold, it freezes, and that leads to a big expansion of the area that's covered by this ice. And typically it can grow to anything between kind of 1 and 2 metres in the Antarctic or 2 and 3 metres in the Arctic. And actually it can get thicker than that as well if it gets pushed together. Bits of ice get pushed together and kind of ridge and form deeper ice. But that ice is very different from, ice that's formed on ice sheets. So an ice sheet is when snow falls and then builds up over several years, decades, even millennia, and you get a very deep ice sheet. Glaciers are kind of the extension of that ice, so flowing kind of rivers of ice. And icebergs would then be the ice that breaks off an ice shelf. So all of those types of ice accumulate from essentially frozen snow that builds up, different from sea ice, which forms when the ocean freezes.
Yeah, so crucially, particularly with sea ice, it's nothing to do with sea level. It's just a property of the sea itself.
Indeed, and it changes each year. So every year you go from not very much sea ice in summer, some remains at the moment, through to lots in winter. And that natural ebb and flow happens each year, but then that natural ebb and flow is also changing.
Nice. Okay. So why is sea ice so important for the Earth's climate system? How is it integrated into everything?
So for multiple reasons. But the first one, in terms of kind of the global climate system, sea ice is really white. So if you imagine the sea freezes and then you get a very cold white surface instead of the dark blue surface of the ocean, and white's reflective. So that white surface, particularly when it's covered by snow, which is even whiter, reflects back the energy from the sunlight from the sun, and reflects back to space sunlight that would otherwise go into the oceans and heat up the oceans more. And so it's kind of a bit of a cooling response. So it helps to keep the planet a little bit cooler than it would be otherwise. And that's important if we think about both poles together. But actually, there's other ways in which sea ice is important as well. So one of them is for the oceans. So if you think about sea ice, because it is part of the ocean, it sits between the ocean and the atmosphere. So when that sea ice forms from seawater, which is salty, most of that salt doesn't go into the sea ice. The salt goes into the water, and salty water is dense water. So that dense water can then sink. It can then contribute to kind of how dense the ocean is in different places. And that forms dense bodies of water, which contribute to kind of the global circulation of the ocean. So it's really critical.
Yeah, so I mean, certainly if we're going to briefly talk about the Antarctic, that you can sometimes see these amazing visualizations where people will show you the view of Earth from the perspective of Antarctica, and you can see that all of the different global ocean currents are actually all connected together as well, and they're drawing from this kind of big circular current that's going around Antarctica. So the relationship between the very cold places and then places that might seem closer to home and the currents that are shaping our weather, for instance, in the UK, are all really closely interlinked and dependent on each other.
Exactly, yeah. That visualisation where you see the Antarctic in the middle makes it obvious it's a global ocean, right? It's not lots of oceans, it's one global ocean. And then sea ice is also important for the atmosphere. So related to that idea of it being cool and reflecting back energy, if sea ice isn't there, then you can warm up locally more. And that's important for things like weather patterns. So the ice effectively, sea ice acts as a bit of a barrier between the ocean and the atmosphere. So it affects how much carbon actually locally is taken up into the ocean. And then that links into what I was saying about ocean currents as well. If that carbon is taken up by the ocean and then goes down into the deep ocean, it's not in the atmosphere anymore. Similarly with heat. So sea ice really affects how much kind of heat and carbon moves between the atmosphere and the ocean. It also affects weather patterns. So because where sea ice is, it's colder than where sea ice isn't. It can affect weather patterns a lot. And also, obviously, it's just really important for creatures. And so thinking about ecosystems, I guess, in the Arctic, polar bears are really heavily affected. And so this year in particular, actually, Hudson Bay has been one of the areas where there's been particularly little sea ice formation. And that really affects the hunting patterns of polar bears. And often it's not just whether there's sea ice there or not, but it's how many months of the year the sea ice is there for that really affects how much food they're able to get, how long they have to kind of wait, essentially, for their food availability to come back. And there's loads of other species that are impacted as well. We like to talk about polar bears because they're the kind of the high profile thing that everyone's seen a picture of a sad polar bear on sea ice. But the whole ecosystems can be affected in similar ways.
So earlier this month, the amount of sea ice in the world went down to its lowest ever amount based on the data that we have. Arctic sea ice is currently breaking records for the amount of ice we'd see at this time of year, and Antarctic sea ice is skating pretty close to the lowest amount that we've seen there. What does this mean in numbers? So over the 5 days to the 13th of February, the combined extent of Arctic and Antarctic sea ice was 15.76 million square kilometres, which is less than the previous low from January 2023, which was 15.93 million square kilometres. So I checked the numbers today, which is about a week later, and we're now at 15.977 million square kilometres. So that's just peaking now above that 2023 low. So just to state the obvious, the vast majority of the ice in that number today in February is made up of Arctic sea ice because it's winter in the Arctic in the Northern Hemisphere. So of that almost 16 million square kilometres of sea ice in the world, 13.9 million square kilometres of that is in the Arctic at the moment. But what you need to know is that is a low number, particularly for the time of the year in the Arctic. Today's sea ice extent in the Arctic is the lowest sea ice extent for this date compared to any other year that we have a record for. And by the way, anyone can look up this data. There's a great graph visualizer on the website of the US National Snow and Ice Data Center, which is the NSIDC. Anybody can go on that website and take a look at that data. So that's what's in the news. Let's dig into what's going on here. All of this has coincided with the warmest January globally observed, and that's after a really warm, record-breaking 2024. Is that related to what we're seeing in the Arctic? What factors are shaping the formation of sea ice?
Yeah, so Arctic temperatures do tend to be more closely related to global temperatures than maybe the Antarctic temperatures too. So the Arctic Ocean is surrounded by land masses, so largely Canada and Russia. And then you've got a couple of areas where the Pacific Ocean and the Atlantic Ocean can kind of access the Arctic Ocean. And so that gives you a picture of what's going to affect how much sea ice is in the Arctic. So first of all, you've got the atmosphere. So how much warm temperatures can get up to the Arctic, and that might be affected kind of locally, or it might be affected by weather systems. So if you get a particular pattern that means you have strong southerly winds, so winds coming from the south up, particularly kind of east of Greenland, east of Iceland as well, coming up into the Antarctic, that can push ice up into the Arctic Ocean and also bring warm weather. And so the atmosphere is important. The ocean's important. So again, how much heat is getting in. So ocean currents, and also kind of what we call feedback, so kind of loops back. So, for example, when I was talking earlier about how bright ice is and how much sunlight it reflects back to space, if early in the summer, as sea ice is melting, you kick that into action, as it were. So you melt some ice earlier and you get melt ponds that are dark that then reinforces back and helps the sea ice to melt more.
I see. So you've got this kind of situation where you've already melted some ice and then that's going to then become locally warmer again because you're not reflecting the sunlight back into space.
Yeah, you're absorbing the heat, yes. Yeah.
Okay. And with the winds that you were talking about that can drive the sea ice northwards, can they be affected by climate in and of itself, or is that just a kind of a yearly variable phenomena?
So largely, it's internal variability. Typically, whenever we talk about anything to do with the climate, if we're talking about something to do with temperature, so what we call thermodynamics, things are warming up, it's quite easy to link that to climate change. Whenever we talk about dynamics, winds, it's a bit harder, but there's often an element that does come from climate. So the key one that's important to think about when we talk about the Arctic is cold, the equator is warm, and that difference in temperatures drives something to do with our weather patterns. So the jet streams are not just driven by the temperature differential, but the strength of the jet stream, so the fast winds that encircle our planet, are affected by that temperature gradient. And so it's plausible, although it's hard to pin down in data, that if you change that difference, because the Arctic has been warming 4 times faster than the global average. And so if you change that difference, because the Arctic was a lot colder than the equator and now it's not so much colder than the equator, then those winds will be affected. And so there are ways in which the climate change and therefore temperature changes locally can affect kind of weather patterns. But as I say, typically they're harder to pin down. Just because the variability naturally is so high as well.
So you just said that the Arctic is warming 4 times faster than the rest of the planet. Is that related to that kind of loss of the white cover in terms of its relative increase in temperature?
Yes, so that's one of the drivers. So we talk about feedbacks in the climate system, which is where climate warms, it changes something, and then that either makes climate warm less or more than it would have done just on its own without that process. And so that sea ice brightness effect is one, and there's a few others as well that are at play in the Arctic.
Okay, that's really interesting because, as you said, the Arctic appears to have been changing much more apparently than Antarctica. Is there a reason why Antarctic sea ice seems to have been impacted earlier by comparison? Is that about something specific about the Arctic or something specific about the Antarctic?
So that's a really tricky one, actually. So if we just go back kind of a second to the timings. So yeah, Arctic sea ice, actually, as long as we've been observing it, has kind of been declining. And then the really big drops started happening. So 2007 was the first time that we had a record summer minimum in the Arctic, and again in 2012. And at that time in the Antarctic, we were still seeing increases. And it was only 2016 through to summer 2017 that we saw the first record minimum in the Antarctic, and then now the Antarctic is at record lows and has been kind of repeatedly at record lows. So that's about a decade, about a decade's difference really in these things happening. And there was quite a lot of kind of research, obviously, particularly when those differences were most prominent as to why. And one reason is just that the Antarctic is so much more variable than the Arctic naturally. And there's also kind of lots of details to do with the ocean and the atmosphere. So geographically, the two are very different. So Antarctica is a continent surrounded by ocean, and then those very fast currents that we were talking about earlier. So in the ocean and in the atmosphere, you've got fast ocean currents circling Antarctica and fast winds as well. Whereas the Arctic is an ocean and a relatively shallow ocean. It's shallower than the Antarctic Ocean, surrounded by land. And so because of that, you get quite different kind of how things can affect, how affected they are by the global versus by kind of local processes and local variability. And so, there's lots of discussion about why the Antarctic was increasing, whether it was just due to that kind of natural variability masking a signal, or whether there was something concrete going on.
So it does seem like there's been this regime change in Antarctica. Do you think we are now kind of past that point where we're going to ever find out quite why it had this delay?
Yeah, that's a really interesting question. I do wonder about that because, we didn't completely answer that question. But obviously, in some senses, the priority now is finding out whether this regime is going to continue, how much. But actually, to do that, we need to understand really what was going on as well, because to help us understand how much of what's just happened is a continuation of that natural variability and how much is really a regime shift due to climate change, we need to be able to understand what had gone before. So we're obviously still looking at that question. It's still really interesting to unpack it.
So returning to the Arctic, it's estimated that the Arctic will be ice-free by 2100. How do you go about estimating something like that?
That's a really good question. First of all, let's unpack what we mean when we say that there'll be an ice-free Arctic by 2100. And first of all, actually, if we're talking about summer sea ice, we expect it to be a lot sooner than that. And so it's likely that the Arctic will be ice-free in summer, in September, somewhere between 2030 and 2050.
Okay. Oh, between 2030 and 2050?
Yeah.
Oh, that's a lot earlier.
Yeah.
Okay, cool. Okay, that concentrates the mind, doesn't it, a bit?
And if we're talking about 2100, then we might expect it to be ice-free for several months of the year. But first of all, we need to understand what do we mean by ice-free Arctic. And actually, we don't mean an Arctic that has no sea ice in summer. We mean typically that there'll be less than 1 million kilometres squared, which is roughly speaking the area of Canada. And that's because we'd always expect some sea ice to remain kind of around the coasts in regions where it's very thick. So 1 million kilometres squared is what we mean by an ice-free Arctic. And typically we mean in summer, in September. And the only way to do that, to make these projections into the future, is by using coupled climate models. So we have coupled climate models, which Climate Science 101, computer models, which take lots of information about what we know about physics, primarily, but also chemistry and biology of what drives the Earth systems. And traditionally, these are ocean and atmosphere. And obviously, the sea ice being part of the ocean is part of that. And these are, if you imagine dividing the ocean and atmosphere into typically big cubes, massive cubes, and then in each of those massive cubes that might be kind of 100 kilometre square on each side, you are using kind of equations that we know control the atmosphere and the ocean to run forward in time how the atmosphere and the ocean will change. And that's used for weather forecasting. It's also used for climate running into the future. If we're doing a climate projection, then we take assumptions about how our emissions might change in the future. And typically we do a few of those. So we say, okay, worst case scenario, we don't make any changes to our lifestyles. We carry on burning as many fossil fuels as we can. Best case scenario, we make quite a lot of changes and reduce our emissions. And so you run forward these computer models under those different cases, and they give you a projection of the future, of a likely future. And there's lots of different models that have been kind of put together. Again, same basic physics, but coded in slightly different ways, slightly different assumptions. And so you get lots of representations of how the future might look. That was Climate Science 101, quite Climate Modelling 101, quite a long one. If you then go back to the sea ice problem, you've then got lots of kind of ideas of how the sea ice is going to change in the future, lots of sets of data of how the sea ice is going to change. And from each of those, you could say, OK, by a certain year, there's not any sea ice left.
So actually, is this a question of probability when you take that kind of selection of different models for the future? Are you saying what do the majority of them look like, or is it like a couple of favoured models when someone comes to this kind of broad brush statement they're willing to put in the media, for instance?
So they'd be based on a lot of models. Typically, they might have taken out, either they'll have selected several, not all, but still several, or they will have given more weight to some. So, you might, if you have they're not opinions, but if you had a series of opinions from people, you might give some people's opinions more weight based on, what they know, what their background is. And so there's statistical ways with climate model output of giving some more weight. So typically one of those things would be done. And then when I said likely earlier, that's a very formal statement actually in the way that I'm using it.
Yeah.
And that's probably attributed to if it's following the language that's used in the big climate reports, that means a 66% probability. So two times out of three that would happen. So so it is very much probability. And actually, at some point, people were, estimating that it could have been really earlier, even this decade. And actually, it's not impossible that there could be a sudden surprise in terms of the year-to-year variability that would then take us closer to reaching that this decade, but likely to be between 2030 and 2050.
Gosh, I mean, if you do go on the kind of Snow and Ice Data Centre website, anybody can look up the extent data for sea ice, and you can plot new layers on this kind of online graph, and it can look at each year's progression. And I have to say, when you look at the Arctic, and you just put the last couple of years in, they are substantially lower than the kind of much longer term averages. So it does kind of put you in the mindset of like things could change very suddenly. And I guess the experience with the Antarctic is that you can have this regime shift that suddenly becomes apparent after a long period of stability as well.
Yeah, and I think particularly with the Arctic, again, what happened in 2007, which is a really long time ago now, but that was what happened then, and in 2012 that we did have this really sudden, I mean, it was already decreasing, but that rate suddenly accelerated. And yeah, those graphs are really striking. You can actually plot each decade. And for the Arctic, that's really striking because each decade is kind of separate. So if you plot the average for each decade, 1980s, 1990s up to today, each decade is distinctly lower than the one before. And so you can see that kind of takes out the noise of each year and things that can vary year to year, but you really see that progression decade on decade, and it's quite remarkable.
Okay, and another nitty-gritty question for you. So when we say this is the smallest recorded extent for the time of year, we're talking about satellite records specifically. So how are we getting this sea ice extent data?
These observations come from satellites, and we've been talking most about sea ice extent. So that's just how much, if you look down at the Earth, how much of the surface of ocean is covered by sea ice. And so they're taken from satellites. It's something called passive microwave. So essentially that means you're not sending a signal from the satellite, you're viewing microwave emissions and using those to calculate how much sea ice is there. And that's been done since late 1978.
Okay, so if I was a climate skeptic, I might say we don't know what's happened prior to the satellite era. So is that actually true?
There are other data before 1979. So the best data we have is from satellites, and that's because they're able to give us a complete coverage. We can see the whole picture. But we do have data before 1979. So things like whaling, actually. One good thing about whaling is that the whaling ships that were going into the Arctic and the Antarctic would take records of how much sea ice they saw. And also, particularly in the Arctic, a lot of the national kind of meteorological institutes or whatever would be measuring how much sea ice. So actually, we're very confident that back to 1850, these levels have not been seen before in summer. So what we've been seeing in recent years isn't just unprecedented since 1979. We're very confident it's unprecedented since 1850. Going further back, it's harder. Obviously, we don't have those measurements. People weren't necessarily going to these places. There are some ways that we can estimate, so using what we call proxies. So that's things like sediments, other things. We can estimate what temperatures were. And from what temperatures were, we can get an idea because of what I said about the link between sea ice and temperature. So that's much less confident, but it gives us some sense that what we're seeing now is probably unlikely on those longer timescales, although it's much less certain. Even if it's not unprecedented, we still have ways of saying that we're confident there's a human influence on this sea ice change. And so, again, going back to climate models, another thing that you can do with climate models is run what we've seen historically. Again, so we know what emissions we've made in the past, so we can run historical runs of climate models. And again, if you do enough of those and if you do them carefully and if you use lots of different models, you can say, well, okay, if we run these models without any emissions, is there any way of getting the kind of sea ice loss that we've seen?
Oh, that's so interesting.
And so it's called attribution. So when you hear people talk about, people do it quite a lot now for extreme event attribution. So was this event affected by climate change? And in the Arctic, we're fairly confident that most, but that means more than 50% of sea ice loss in the Arctic has been due to human influence since 1979. And the rest, as I was mentioning earlier, to do with internal variability of the climate.
Well, that's so interesting. So the same models that are predicting the future, you can actually use to almost check your working against reality.
Yeah, you can use to get an idea of what could have happened, I guess. Yeah, what could have happened in an alternative reality. And that can give you an idea of just how much of what we've seen was due to our own actions.
So if we could potentially be seeing an ice-free Arctic as early as the 2030s or 2050s, is there really anything we can do about that now?
A lot of that early stuff, so particularly if we're thinking about 2030s, 40s, that's kind of baked in. So in terms of whatever emissions we do very soon, it's hard to change that real near term. What we expect to happen in the next couple of decades isn't really strongly affected by which of pathways we follow. And the Arctic's already changed. But longer term, we really do have the agency to change this. And so particularly if you look at the end of century, there's a big difference between how much sea ice will be left in the Arctic if we, particularly in other months of the year as well. So I was talking about that season length, how long the sea ice is there for each season. That's really strongly affected by whether we emit an awful lot of greenhouse gases or less greenhouse gases. And so we do have agency to change that. And actually, in an amazing world where we manage to go net zero or reduce the amount of carbon in the atmosphere, ultimately that sea ice could recover. The kind of futures we're looking at, we're probably not going to get to that point. But theoretically, sea ice could recover in the Arctic. It's not baked in. And so we certainly have agency to slow down the rate of change and to somewhat limit how big those changes are.
That's a really nice note to end on, actually, because there's so many topics in polar science where some of the answers are a little bit more depressing, and actually to have such an important aspect of the kind of global climate still within our power to change, I think is really encouraging. So yeah, so that's the message we need today.
Definitely. Yeah.
Great. Thank you so much for coming on the podcast.
Thank you.
Thanks for listening to this episode of Beyond the Ice. If you're interested in learning more about sea ice, you can go back to episode 1 of the Beyond the Ice podcast and listen to the interview with Dr. Ella Gilbert, where we really dig into what's happened in the Antarctic and what might have caused that sudden change in sea ice extent that we saw around 10 years ago. If you enjoyed this episode and found it useful, please do share it with your friends and family or colleagues. You might even consider going on Apple Podcasts and leaving us a review. It's one of the best ways to help new people find this podcast. See you next time.